Right now, inside a steel factory in a Chinese city most people have never heard of, a machine is running that the world's top engineers have been trying to build for over 60 years. It is not powered by coal. It is not powered by gas. It does not burn anything at all. It runs on the same stuff coming out of your mouth right now. And in its first few months of operation, it has already produced 70 million kilowatt hours of electricity from energy that used to disappear into thin air. Literally into thin air. Gone. Wasted. Every single day. For decades. Here is the part that should really get you. The physics behind this machine was figured out in 1872. Engineers have known for more than 150 years that this was possible. And for most of that time, it seemed like the kind of idea that sounds brilliant on paper, but could never actually be built in the real world. China just built it. On December 20th, 2025, a machine called CO2 went live on a real power grid inside a real industrial facility, generating real electricity that flows into real homes. For the first time in history. And the reason this matters is not just what it does today. It is what it tells us about what comes next. Stay with me on this, because by the end of this video, the way you think about how electricity gets made is never going to be the same. Section 1. The dirty secret, hiding inside every light switch. Every time you flip a light switch, something spins somewhere in the world. A turbine, always a turbine. Does not matter if your power comes from coal, gas, oil, or nuclear energy. Does not matter if you live in New York or Tokyo or Lagos. The final step before electricity reaches your home is almost always the same process. Heat something up. That heat makes fluid move. The moving fluid pushes against blades. The blades spin. Spinning makes electricity. That is it. That is the whole secret behind the modern power grid. And here is what should actually bother you once you hear it. The core idea has not changed since the 1880s. We are still using a system that was figured out before cars existed, before airplanes, before anyone had heard of a computer chip or an antibiotic. The basic logic of how most of the world's electricity gets made was locked in while people were still riding horses to work. We call it the steam turbine. You heat water. The water boils into steam. The steam rushes through spinning blades. The blades turn a generator. Done. Victorian. Simple. Now, before you think, okay, but we must have made it way better over time. Yes, we absolutely have. Modern steam turbines are incredible machines. Some of the turbine blades inside them are made from single crystals of metal that are grown one atom at a time in a controlled furnace. A regular metal grain structure is not strong enough for what they have to survive. The temperatures inside the hottest steam turbines can melt most metals you would find in any hardware store. The engineering is extraordinarily precise. In the 1970s, industrial steam turbines were already running at temperatures of 650 degrees Celsius and pressures of 34,500 kilopascals. Engineers have spent 140 years squeezing every last drop of performance out of this idea. Every decade, better materials, better designs, better everything. And after all of that effort, after 140 years of the world's best engineers working on this exact problem, the average efficiency of a thermal power plant in the United States sits at around 39% as of 2023. Let that number breathe for a second. 39%. That means that out of every unit of energy you put in, whether you got it from burning coal, burning gas, or splitting uranium atoms, roughly 60% of it just gets thrown away. It goes into the air. It warms a river. It heats the atmosphere around the cooling towers. Gone. Not turned into electricity, not used for anything. Just wasted. Think about that in the most practical way possible. You own a power plant. You buy fuel. That fuel costs real money. You burn it. And more than half of the energy inside that fuel never makes it to a single home, a hospital, a school, or a factory. It just disappears into the sky. And we have been doing this every single hour of every single day for over 100 years across every country on Earth. The numbers at a global scale are almost too big to hold in your head. The world burns billions of tons of fuel every year to make electricity. If even a meaningful fraction of the energy being thrown away as waste heat could be captured and turned into power instead, the impact on fuel costs, on carbon emissions, on electricity prices would be enormous. Not a small improvement. Enormous. Engineers have known this for a very long time, not as some abstract concern that pops up in academic papers, as a real and practical obsession. For generations, brilliant minds in thermodynamics and materials science have been searching for something better than steam. A smarter fluid, a smarter cycle, a system that could squeeze more electricity out of every bit of heat instead of dumping 2/3 of it into the atmosphere and calling what is left a success. They kept landing on one answer, and the substance at the heart of that answer is something you make yourself, roughly 20,000 times every single day without thinking about it. Section 2. The weird science nobody taught you. In school, the machine that just changed history runs on carbon dioxide. And yes, I can already hear you. Carbon dioxide is the greenhouse gas. It is what we are desperately trying to emit less of. Using it to generate electricity sounds like a bad joke. But here is the thing. This machine is not burning CO2. It is not making more of it. It is using CO2 the same way a steam turbine uses steam, as the working fluid, the thing that actually moves through the turbine and does the work. Think of it as swapping out water for a completely different substance that happens to work far better for the job. To understand why CO2 is so good at this, you need to know about one of the stranger things physics can do. And it is genuinely strange. Most people never hear about it in school, even though scientists have understood it since the early 1800s. You were taught that every substance has 3 states: solid, liquid, gas, ice, water, steam, 3 clean boxes. But there is actually a 4th state that only shows up under very specific conditions of temperature and pressure. And when a substance reaches it, something deeply weird happens. The liquid and the gas stop being separate things. They merge together into one single state of matter. Scientists call it the supercritical state. Try to picture it this way. Normally, a liquid and a gas have totally different personalities. A liquid is heavy and dense. It flows slowly and stays in a definite space. A gas is light and spread out. It fills whatever container you put it in and moves freely. They look different. They feel different. They behave completely differently. But past a certain temperature and pressure, a substance becomes both at once. Dense and heavy like a liquid, but flowing freely and easily like a gas. It is a phase of matter that sits completely outside the 3 you learned about. And it is completely real. You can actually watch it happen in a lab. Heat and pressurize a sealed container of CO2 past the critical point, and the line between the liquid and the gas, the visible boundary between them, just disappears. The 2 phases blend into one. No border. One fluid. Now here is where CO2 becomes almost unfairly good compared to water. For water to reach that supercritical state, you need to heat it to 374 degrees Celsius and crush it under about 220 atmospheres of pressure. That is brutal. That is genuinely difficult to engineer. It destroys equipment. It requires exotic alloys just to safely contain the water. Building machines that survive those conditions is one of the main reasons advanced steam turbines are so expensive and hard to maintain. Carbon dioxide reaches its critical point at just 31 degrees Celsius and around 73 atmospheres of pressure. 31 degrees. That is a warm afternoon at the beach. The pressure requirement, while not nothing, is dramatically lower than what water demands. Compared to the engineering challenge of supercritical water, getting CO2 into its supercritical state is almost embarrassingly easy. And once CO2 crosses that threshold, it develops properties that seem almost custom-made for generating power. It becomes nearly as dense as liquid water, but it flows through pipes and turbines with the smooth ease of a gas, dense and heavy on one hand, fast and free-flowing on the other, at the same time, in the same fluid. That combination is the combination that makes turbines work well. Here is the key. In any turbine, the more mass you can push through the spinning blades every second, the more power you extract. Steam is not very dense. To generate serious amounts of power from steam, you need a machine with enormous blades, enormous pipes, enormous cooling systems. The turbine halls in major power plants are literally the size of aircraft hangars. The pipes feeding them are wide enough for a person to walk through. The whole system is massive and expensive because you need all that size to compensate for the fact that steam just does not have much mass packed into each unit of volume. Supercritical CO2 is so dense that you can push a massive amount of mass through a machine that is a tiny fraction of the size. The engineers at Southwest Research Institute in San Antonio have stated that a desk-sized supercritical CO2 turbine could theoretically power 10,000 homes. A desk-sized turbine. That is not a typo. That is not a rounding error. That is the physics of working with a fluid that is extraordinarily dense. The whole power block shrinks. The pipes shrink. Everything gets compact in a way that steam-based systems simply cannot match. And then there is efficiency. The way the thermodynamics work inside a supercritical CO2 system, far less energy gets lost along the way. Well-designed supercritical CO2 cycles can reach over 50% efficiency. The best conventional steam setups hit around 35 to 40% in real-world industrial conditions. That gap is not a marginal improvement. That is a completely different league. Scientists figured all of this out in theory a long time ago. The cycle that supercritical CO2 turbines rely on was described in 1872. Researchers were seriously exploring CO2-based power generation as far back as the late 1960s. The theory has been sitting there for over half a century, basically waving its arms and saying, "Build me, this works." So why did it take until December 2025 for anyone to actually do it? Because building this thing in the real world was one of the hardest engineering challenges of the last 60 years. Section 3. The three walls that stopped everyone. There is a reason it took 60-plus years to get from a good idea on paper to a machine running in a steel plant in China. There are three separate engineering problems that all had to be solved at the same time, not one after the other, all at once, and each one of them was enough on its own to stop most teams cold. The first wall is what the hot CO2 does to the metal it lives inside. To get the best efficiency out of a supercritical CO2 system, you need to heat the CO2 to around 700 degrees Celsius before it hits the turbine. That number might not mean much until you understand what metal does at that temperature. At that level of heat, under sustained pressure, metal does not stay where it was put. It slowly moves. This is called creep. A bolt under heavy load at 700 degrees does not stay the same length. Over months and years of continuous operation, it very slowly gets longer. A turbine blade running for thousands of hours at extreme heat and pressure is not quite the same shape it was when it was installed. And in a machine where the parts have to be precisely fitted with almost no tolerance for error, even tiny dimensional changes can create problems that are catastrophic. But the CO2 itself adds another attack on top of that. At high temperatures and pressures, CO2 starts forcing carbon atoms into the grain structure of certain metal alloys. Over time, this changes how the metal behaves. It starts to become brittle. A turbine blade that begins its life tough and flexible and gradually becomes fragile, while spinning at tens of thousands of rotations per minute inside a pressurized closed loop, is a blade that can fail in sudden and violent ways. The material solution requires special alloys designed at a microscopic level to resist both the creep problem and the chemical attack from the CO2 itself. These alloys exist. They work reasonably well, but they cost many times more than regular steel. And because no system has run for 20 or 30 years in continuous commercial conditions yet, nobody has a complete picture of how they will hold up over the full lifetime of a plant. That lingering uncertainty makes investors nervous. Nervous investors means slower funding. Slower funding means slower development. It is a frustrating loop that the industry has been stuck in for decades. The second wall is the heat recycler, and this one is arguably even more mind-bending. One of the main reasons supercritical CO2 systems are so much more efficient than steam is that they capture heat from their own exhaust and feed it back into the incoming fluid before it even reaches the main heat source. The system basically recycles its own waste warmth before asking for more energy input. Think of it like this. Before the cold fluid enters the hot part of the system, you pre-warm it using the heat from the fluid that just came back from the turbine. You use the energy you already have twice before you ask for more. This recycling step is responsible for a huge chunk of the efficiency advantage. But to make it work at the level required, you need to transfer an enormous amount of heat across an incredibly thin wall, while both sides of that wall are sitting at pressures approaching 200 atmospheres. 200 atmospheres is roughly the pressure you would find at 2,000 meters below the surface of the ocean. The hardware needed to handle this is unlike anything in conventional power engineering. Engineers chemically etch channels into flat metal plates. Some of those channels are narrower than a single human hair. They etch millions of them across thousands of plates and then fuse all those plates together into one solid metal block with an intricate web of microscopic flow paths running through it. The result is a device that is compact, incredibly strong, and extraordinarily effective at moving heat between two fluid streams through walls that are barely there. But it is also essentially impossible to inspect once it is assembled. You cannot take it apart for maintenance without destroying it. You cannot reach inside to check for cracks. If something goes wrong anywhere inside that block while it is sitting under 200 atmospheres of pressure, the result is not a gentle warning sign. Building these heat exchangers reliably and proving they will stay intact for decades of continuous operation has kept engineers awake at night for years. The third wall is speed. Because supercritical CO2 is so dense, the turbine can be made physically small. That is one of its greatest advantages. But here is the trade-off. Small turbines need to spin faster to extract the same amount of power from the fluid moving through them. Much faster. A car engine at highway speeds runs at around 2,000 to 3,000 rotations per minute. The turbines in a supercritical CO2 system can spin at 10 times that speed or more. At those speeds, regular bearings with oil lubrication simply cannot cope. The friction generates so much heat that conventional bearings fail within hours. So engineers had to develop entirely new solutions. Magnetic bearings that hold the spinning shaft in place using precisely controlled magnetic fields, with no physical contact between moving parts at all. Or bearings that float on a thin film of the CO2 itself, using the pressure of the working fluid to keep surfaces apart. Both approaches work in controlled lab environments. Both have been shown to handle the forces involved. But neither had been proven over decades of continuous industrial operation in a demanding real-world setting. That lack of long operational data is exactly what keeps engineers cautious and keeps new technology out of critical infrastructure. 3 walls, materials, heat exchangers, bearings. All 3 had to be solved at the same time, and all 3 had to keep working, not for a few test hours in a laboratory where someone can hover over them and make adjustments, but continuously for months and years in conditions that no lab can fully replicate. That is what made this so hard, and that is exactly what makes what happened in December 2025 so significant. Section 4. The machine that crossed the finish line. The city is Liupanshui in Guizhou Province, southwest China. A city built around coal and steel, the kind of heavy industrial city that most people outside China would walk straight past on a map. On December 20th, 2025, something happened there that engineers had been trying to make happen for over 60 years. A supercritical CO2 power generation system called CO-TAN-1, which you could translate as Supercarbon-1, began commercial operation. It was developed by the Nuclear Power Institute of China under the China National Nuclear Corporation, known as CNNC, and it became the first commercially operating, grid-connected supercritical CO2 power system in the history of the world. The Nuclear Power Institute of China began their research into this technology back in 2009. They achieved stable power generation in a lab setting in 2019. Construction on the commercial demonstration started in 2023, and then, after 16 years of research and development, they crossed the finish line that no one else had crossed. The location is telling. CO-TAN-1 is not replacing a coal plant. It is not powering a city. It is doing something that is, in terms of industrial logic, beautifully elegant. It is catching energy that was already being thrown away and turning it into electricity. Steel production involves a step called sintering. You take powdered iron ore and other materials, place them on a moving grate, and apply intense heat to fuse them together into the right form for the blast furnace. This process generates huge volumes of very hot exhaust gas. Historically, that gas was cleaned for pollutants and then vented into the atmosphere. The heat inside it just went into the sky. Free energy, already paid for by the fuel burned in the steel-making process, disappearing every single day. CO-TAN-1 intercepts that exhaust. The hot gases from the sintering process flow through heat exchangers. Those heat exchangers transfer the thermal energy into CO2. The CO2 gets pushed past its critical point, becomes supercritical, and then goes blasting through a turbine at high speed. The turbine spins a generator. Electricity comes out. The CO2 loops back, gets cooled, gets compressed, and goes around again. The steel plant's production is completely unchanged. Same workers, same process, same product going out the door. The only difference is that a smarter machine is now sitting in what used to be the waste heat exhaust loop. The results that CNNC announced were striking. CO-TAN-1 delivers more than 85% higher power generation efficiency compared to the conventional steam-based waste heat recovery system it replaced. Net power output is more than 50% higher over the course of a full year. The system generates an additional 70 million kilowatt-hours of electricity annually from heat that the factory was already producing and had been throwing away for years. 70 million kilowatt-hours. That is roughly the annual electricity consumption of around 6,000 average American homes. All from heat that was already free. Already there, already being wasted every day. And then something even better happened. By May 30th, 2026, the second 15-megawatt unit came online at the same site. The full 30-megawatt system is now running. Both units have been operating stably for months. Every performance indicator has met or exceeded its design targets. CNNC stated that the long-term operation has validated the reliability of the core equipment and the stability of the overall system under a range of real operating conditions. That last sentence matters more than it might seem. There is a massive gap between a laboratory demonstration and a commercial deployment. It is not a small step. It is a completely different category of engineering challenge. Supply chains, regulatory approvals, industrial reliability standards, the need to keep running without anyone standing over it making constant adjustments, real-world conditions that no lab can fully replicate. CO-TAN-1 has cleared all of that. And with the second unit now running, and both units performing as designed after months of actual industrial operation, that changes the conversation around this technology in a way that cannot be walked back. CNNC Chief Scientist and Chief Designer Huang Yanping described the project as representing the first global transition of this technology from laboratory to commercial implementation. What makes that statement matter is not the language. It is what it means in practice. And what it means is that the clock has officially started. It is also worth being clear about one thing. The detailed engineering specifications of CO2 have not yet been published in independent, peer-reviewed scientific journals. The performance numbers come primarily from CNNC announcements and Chinese state media. Until those numbers are fully independently verified, a small amount of healthy caution about the exact headline figures is reasonable. But here is the thing that no degree of caution changes. The machine exists. Both units are connected to a real power grid. They are running in a real industrial facility that operates every day because it has to. A steel plant cannot pause its operations because a piece of equipment is underperforming. Products need to ship. Contracts need to be filled. The machine is either working or it is not. And it is working. An independent expert panel, led by members of the Chinese Academy of Engineering and the Chinese Academy of Sciences, reviewed the project and declared the technology internationally leading overall. That is not a marketing claim. That is a technical judgment from the kinds of people who know what they are looking at. Section 5. Why this changes everything that comes next. The steel plant in Guizhou was not chosen at random. It was chosen deliberately as a first step, and understanding why reveals a lot about where this technology is actually heading. A waste heat recovery system at a steel plant is, by the standards of critical energy infrastructure, a low-stakes starting point. If CO2 develops unexpected problems, needs more maintenance than planned, or gets taken offline for adjustments, the consequence is that one factory earns less bonus electricity. No city loses power. No grid gets destabilized. No hospitals go dark. This is exactly the right way to introduce a fundamentally new technology into the world. You start somewhere where the cost of failure is manageable. You gather real operational data. You build a track record. And then, with that track record in hand, you approach the applications that actually matter most. CNNC is already moving to the next step. In 2024, the organization launched a second demonstration project that combines molten salt energy storage with supercritical CO2 power generation. That project has been selected as part of China's national program for first-of-a-kind energy equipment. Deployment is expected by 2028. That is not a research project. That is a scaling roadmap. Now let us talk about where this technology goes when it is mature enough to be trusted in the places that matter most, because the list of applications is genuinely remarkable. Nuclear power is probably the most transformative application on the horizon. Right now, nuclear plants generate electricity using steam turbines, the same basic process as coal plants. The heat source is different, but the last step is identical. Boil water, make steam, spin a turbine. This means nuclear plants need all the same colossal turbine halls, all the same enormous cooling systems, all the same massive infrastructure footprint. Supercritical CO2 cycles are a recognized power conversion option for future nuclear reactors, and the way the physics work, the high operating pressure dramatically reduces the size of the components needed. This makes it a strong candidate for the next generation of compact nuclear systems. A nuclear plant built around a supercritical CO2 power system could be dramatically smaller than a conventional plant for the same power output. And smaller means cheaper to build. Cheaper to build means nuclear power becomes accessible in places where the economics of a full-size reactor make no sense at all. Small modular reactors are one of the most talked about developments in energy right now, precisely because of their potential to be compact and cost-effective. Pair them with supercritical CO2 turbines and you start to get nuclear power plants that could potentially be deployed in smaller grids, in remote locations, or in countries that could never afford a conventional gigawatt-scale nuclear facility. That changes the global energy picture in ways that are genuinely hard to fully imagine right now. Then there is shipping. The world's commercial fleet moves essentially everything you own. Every piece of electronics, every item of clothing, every food product that traveled more than a few hundred miles to reach you came on a ship at some point. Those ships burn massive amounts of fuel. A supercritical CO2 power system offers not just efficiency gains, but also the compact footprint that is incredibly valuable on a vessel where space is always at a premium. Research published in 2025 explored replacing conventional steam cycles on nuclear-powered vessels with supercritical CO2 systems, and found efficiency gains approaching 49% for the CO2 system compared to advanced steam alternatives, almost half again as much electricity from the same heat source, on a platform where generating more power from the same engine or carrying less fuel for the same journey matters enormously. Then there is concentrated solar power. This is the form of solar energy that uses mirrors to focus sunlight onto a central point, creating intense heat that then drives a power cycle. In places like the Middle East, North Africa, the American Southwest, and the Australian outback, the solar resource is extraordinary, but those regions also tend to be very dry. And conventional solar thermal plants using steam need significant amounts of cooling water to operate efficiently. Supercritical CO2 systems can operate with dramatically less water than steam-based power cycles because the CO2 stays in a closed loop and the cooling requirements work differently. That single advantage could open up enormous sun-drenched regions to serious solar thermal power generation in ways that steam simply cannot achieve. Huang Yanping explicitly identified solar thermal as one of the future application areas for this technology, alongside energy storage and broader waste heat recovery. And that brings us back to industrial waste heat, which is probably the nearest term application as this technology scales. Steel, cement, glass, chemicals, aluminum, refineries. The industrial world is full of processes that generate enormous amounts of heat as a byproduct. Most of that heat currently goes into the atmosphere. If even a fraction of it could be cost-effectively captured by supercritical CO2 systems and turned into electricity, the effect on industrial energy costs and carbon emissions would be significant. Not a footnote, not a rounding error, a meaningful fraction of global industrial energy consumption potentially recovered from processes that are already happening anyway. And the United States is not standing still in this race. Southwest Research Institute in San Antonio has been collaborating with GTI Energy and the U.S. Department of Energy to design, build, and operate a 10-megawatt supercritical CO2 pilot plant at their headquarters, a $155 million facility. Germany, South Korea, and Japan all have active research programs at various stages of development. But China moved from research to real commercial deployment first. And the way technology development works in practice, that lead is not just a symbolic win. Every hour that K010-1 runs in that steel plant, it is generating a kind of data that no laboratory in the world can produce. Data on how the materials hold up under months of sustained industrial load. Data on how the bearing systems perform over long periods of continuous operation. Data on whether the heat exchangers develop any unexpected behavior over time. Data on how the control systems manage extreme pressures and temperatures across real operational cycles. That data feeds directly into the design of the next system. The next system will be better and more trusted. It will generate more data. And the one after that, better still. This is how technology curves work. They look flat for a very long time. And then they do not. The steam turbine did not change the world the moment it was invented in 1884. It changed the world when it was reliable enough, cheap enough, and proven enough to be trusted everywhere. In ships crossing oceans, in factories driving the Industrial Revolution, in power plants that eventually electrified every corner of the developed world. That transformation took decades of incremental improvement, of real-world operational experience, of engineering refinements that only come from building things and running them until you understand everything that can go wrong and how to fix it. Supercritical CO2 turbines are now at the very beginning of that same process. The theory has been understood for over half a century. The laboratory demonstrations have been done. The hard engineering walls have been climbed well enough to get a commercial unit running and operating stably in a real industrial facility for months. The data is starting to accumulate. The remaining challenges around materials over decades of operation, around heat exchanger longevity, around bearing systems at scale, our real and honest engineers will tell you that a new power technology needs 10 to 20 years of real-world runtime before it earns the kind of trust required for critical infrastructure deployment. That clock is now running, but for the first time, it is running for real. Not in a controlled laboratory, not in a test rig that runs for a few hours and gets taken apart. In a steel plant in Guizhou where the machine has to perform because the factory cannot afford for it not to. On a real power grid, in real weather, under real industrial conditions, day after day, month after month. The machine that quietly switched on in December 2025 is small by the standards of what power technology could eventually look like. Two 15-megawatt units, a total of 30 megawatts. Enough electricity for a relatively modest number of homes, a single steel plant getting more value from its waste heat. But the significance is not the size. The significance is the proof, and the proof is now undeniable. The steam age is 140 years old. The technology that might replace it is now running. And the thing it runs on is the same thing you produce every single time you breathe out. If you made it this far, you already know this stuff matters. A like helps more people find this video, and a subscribe with the bell means you will not miss the next one. We cover shifts like this the moment they happen and go deeper than the headlines. Here is my question for you. If supercritical CO2 turbines become the new global standard over the next 2 decades, which industry do you think benefits the most from this? Nuclear power, shipping, industrial manufacturing, or something nobody is talking about yet? Drop your answer in the comments. Those discussions are always worth reading.